slow with a very low magnitude, but there are going to be bigger perturbations on those little features. So this relies on something that we call adversarial gradients, which is this first part. It's the sensitivity estimation. What this does is it starts introducing different perturbations, and you can see how the output is changed based on those perturbations. And the direction of your attack, which is going to be this part, is going to be in this direction. So the one that produces the most change with respect to the change of your feature. So if you see that there's a big change in the output here, then you do your attack there. Okay. And then of course, if you want it to be 4, you optimize this so that if this is a 1 and you want it to produce a 4, then you repeat this until you find the optimal perturbation for a 4. Yes?
Are they using the surrogate function to do the sensitivity estimation?
No, here they assume that they have access to weight, but the procedure is equivalent. So you have a surrogate model, you do it with the weights of the surrogate model. Okay? In the end, the perturbation is on the features. So you do this small perturbation until you get the feature that gives you the change towards the class that you want. Okay? And then once you find it, you get your adversarial sample. Make sense? Sounds easy. This can take a long time, but it is something that can be done. So I'm going to skip a bit the way that they present the paper, because they make a bit of a long explanation on distillation, but we already know what that is. And another interesting part is how they define robustness. So they make up their own metric for robustness. I think it's a fair one, but still it's their own metric, which is that one. So what they call the robustness of the the robustness of the network is defined as an expected value over all the samples over all the perturbations that are going to produce a change in the classification. Okay, so if you found all these perturbations, but that one is the one closest to that, then this is going to be the adversarial robustness, so to speak. And then you take the expected value over your whole training set, and that gives you the robustness. Okay? Or over all the classes, and that gives you your robustness. This is important to keep in mind because it's what they're going to use later to show that distillation actually gives a lot of robustness to adversarial attacks, and the numbers are pretty different. So that's important. And another interesting thing about the paper is that they define what they want. The defense mechanism to do. So the first thing they want to do is have a low impact on the architecture, and low impact on the architecture simply means that you don't want to include new things into the model to make it more robust. You want ideally to have the same model, which is deployable, and you've tested and it works. You want the same model to also be more robust. You want, of course, to maintain accuracy. You don't want a massive drop in accuracy just to be more robust. You want to maintain the speed of the network, which means that you don't want the network to be much larger than it is at the moment. And of course, the defenses should work for samples that are relatively close to the training data set. And this makes sense because if you try to optimize for all the possible adversarial attacks, the problem becomes unnecessarily complicated, and it becomes non-practical, because if an adversarial attack is so different that a human can tell the difference, so if you imagine a spam email, and then your adversarial attack makes it completely impossible to read, then it misses its target, right? You want the modifications to be as small as possible. So we want our system to be robust against samples that are close to the actual sample. Okay? Is that clear? Yeah? Cool. So now let's see what they call defensive distillation. So if you recall from our previous papers, distillation relies on something called temperature. So temperature is in the softmax layer, and So if these are the gadgets, if you want the output I for f, so fi of x is going to be the exponent of set I, which is the output of that, divided by the temperature coefficient over the sum 0 to n-1. Sorry, I should call this L. E to the power z L over T. Okay. And that is called the temperature coefficient. And what happens is that as T tends to infinity, the model will try to make all the softmax outputs as high as possible, which means that they will be of size. So as T tends to infinity, Fi of x will tend to 1 over n.
After the model has been trained. Yeah.
Well, during training, it's
But
going to try to put that
training,
penalty.
You would expect that the Zi also grow in size, right? So if I train at 2 different temperatures, I would expect that the Zi's have a different relationship to each other.
Yes, but
That's why I think if you do it at the same time, the temperature during training doesn't matter at all.
yeah, no, it does. It does matter during training. So it matters during training because, well, it is explained quite elegantly here. Okay. So basically, if you have the hard targets, your cost function becomes this, which is forcing your network to learn overconfident predictions. So it is forcing your network to learn that that is 1, and all the rest are 0. When you have soft targets, now that's your cost function, and oh yeah, I see what you mean. Yeah, no, but you have the hard targets at the beginning, right?
Sure. But I would, yeah, the temperature during training shouldn't affect your test or error or your training. I think.
It does not affect your error, but it does affect your prediction. So it affects the shape of the output. So your accuracy is maintained in a sense. In practice, you have to train for longer because the temperature makes the gradient smaller. But the shape of the output is going to change.
No, I don't think so.
Yeah, it does.
Yes, it's clearly if you increase the temperature, then you're going to increase the slopes of the software.
But then if the Z's become equally as big, so if you just rescale everything by
Well, it's not just rescaling, is it? Because you're dividing you by normalization coefficient. If you make all the values pretty much the same,
yeah.
because as t tends to infinity, okay, e to 1 over the infinity is e to the 1, so all the values will tend towards 1. If all the values tend towards 1, then you divide them by the number you've got.
But that is if the Zi's stay the same. But if I make all the Z's 10 times larger and the temperature 10 times larger, then that effect completely cancels.
Yes, you can rescale it for sure, but that doesn't happen when you do stochastic gradient
But
descent.
when you train, you rescale essentially the activation there, don't you?
No. You don't. Not generally speaking, unless you've got most of the norm of the weights, you generally stay the same, and the norms of the activations generally stay the same through the course of training.
Really?
Yes.
That seems magical.
I think isn't that the case where you don't use that